Welcome back to the Explainer. If you're out there dealing with massive offshore motors, you already know the deal. These things don't usually just blow up instantly, right? Nah, they fail slowly. They cook. You get a prolonged start, a tiny overload, maybe a stalled rotor, and boom, heat builds up in the windings until the insulation literally gives up the ghost. So what's standing between your multi-million-dollar motor and a catastrophic burnout? One incredibly smart little aluminum box, the ABB ACS6000c numerical relay. Today, we're cracking open the mathematical core of this thing. We're going to see exactly how it prevents those agonizingly slow motor burnouts. Let's get into it. Okay, first things first. The SPM150C isn't just sitting there mindlessly watching current. I mean, if it did, it'd just be a basic overcurrent relay, right? Instead, it tracks a totally invisible gauge. It's basically running a continuous mental model of the motor's internal temperature. Think of it exactly like the fuel gauge on your car's dashboard, but instead of tracking gas, it's tracking thermal capacity from 0 to 100%. As the motor runs hot under an overload, this virtual gauge fills up. Hit 100%, the relay trips. When the motor gets a breather, the gauge slowly empties out. So, how exactly does it calculate that heat? Well, let's dive right into the mathematical heart of the overload state. The core heating equation is theta equals I over 1.05 times I minus theta, all squared, times 1 minus e to the power of negative t over tau times 100%. Now, I know that sounds like a mouthful, but it perfectly models the physical reality of hot copper. As current pumps through, the heat builds up super fast at first, and then kind of tapers off as it gets closer to its maximum thermal limit. Let's actually break down those variables so we're not just staring at alphabet soup. I is easy. That's just your actual measured current flowing into the motor. Then we've got I theta. This is your set full load current, which you, the engineer, can actually adjust anywhere from 0.5 to 1.5 times the motor's nominal full load current. But check out that little 1.05 baked into the denominator next to I theta. That is a built-in 5% margin. It's a lifesaver, really, because it makes sure the relay isn't constantly inching toward a trip just because the motor is running right at its normal full load. And finally, there's tau, the thermal time constant. Which brings us to Section 1, Unlocking Tau, the thermal time constant. If you want to know exactly how long your motor can take the heat before that virtual gauge hits 100%, you've got to understand tau. Tau dictates the shape and the speed of the entire heating curve. And it isn't just some random number a programmer guessed at, it's physically tied to your specific motor. The relay calculates it like this. Tau is approximately 32 times T6x. And T6x? That's your motor's maximum safe stall time, literally a countdown clock for a locked rotor. You just grab that spec straight off the motor's datasheet. It tells you how many seconds that rotor can sit there pulling massive current before it destroys itself. Now, the magic here is really in that heuristic multiplier, 32. By multiplying the safe stall time by 32, the relay seamlessly scales its internal math to match your exact machine. So a massive motor with a longer safe stall time automatically gets a bigger thermal time constant. The relay mathematically understands that a heavier, beefier motor can absorb that overload heat for a longer stretch before it absolutely has to step in and trip the circuit. It's just a brilliant piece of scaling logic. But hey, what happens when the overload actually stops? How does the relay know to stop adding heat and start draining that virtual gauge? Well, the SPM150C has a very specific mathematical cutoff for the stopped state. The moment the actual current drops below 12% of the motor's nominal current, the relay says, okay, we are fully stopped. At 12%, you aren't doing any real mechanical work anyways, so the logic instantly flips from the heating phase to the cooling phase. And that brings us to the cooldown. Just like heating, cooling is completely exponential. It just works in reverse. The equation is theta equals theta 0 times e to the power of negative t over kc times tau. You hear that same exponential e curve in there? That perfectly mimics how a scorching hot object cools down in real life. It sheds heat super fast at first when it's blazing hot, and then brutally slowly as the copper creeps closer to ambient temperature. Let's unpack those cooling variables really quick. Theta 0 is just your starting point, whatever percentage the heat gauge was sitting at the exact second the motor stopped. But the real star of the show here is Kc, the cooling multiplier. Think about it. When a motor stops, its shaft-mounted cooling fan stops spinning too, right? So a dead motor takes way longer to cool down than it took to heat up. The Kc multiplier lets you stretch that cooldown curve out. It ranges from 1 to 64 times tau, which directly controls just how agonizingly slow that thermal capacity drains away. So let's put all this math to the test with a real offshore scenario. Picture this. You're on the rig. A critical pump motor trips on a thermal overload.
The process is down, alarms are absolutely screaming, and an impatient operator runs up to the panel and tries to smash the restart button just 30 seconds later. What happens? Does that thermal capacity gauge instantly reset to 0 the second the breaker opens?
The answer is a hard, absolute no. Thermal capacity cools exponentially. It never resets instantly. Because of that cooling equation, the one governed by Kc times tau, it can take many, many minutes for that gauge to drain back to a safe level. If the gauge was pegged at 100% when it tripped, after 30 seconds, it might only be down to like 98%. The relay will explicitly block that restart. It literally acts as an invisible shield against operators who would otherwise fry the windings by forcing a start while the copper is still dangerously hot.
So to quickly summarize the whole life cycle of this thermal model, Step 1. During an overload, the heat gauge fills up based on the ratio of actual current to your set I theta, all scaled by the time constant tau. Step 2. Once the current drops below 12%, the motor is officially stopped, and the cooldown relies entirely on your Kc multiplier to slowly drain the heat. You now officially understand the mathematical heart of the SPM150C, which means we're ready for Step 3, actually dialing in those numbers.
You've got the theory down. You know the formulas. But when you're standing in front of the actual relay during commissioning, every single one of those abstract variables needs a real physical number entered into it. And that leads me to a pretty critical question. What happens if you take these formulas and set those parameters with absolutely zero margin on a real spinning offshore motor? Spoiler alert, you get operators yelling at you because the motor won't stay running. We're going to uncover exactly why that happens and how to master those physical dials to prevent nuisance trips in Part 2 of our explainer on the SPM150C adjustment setting ranges. You definitely won't want to miss it.